Hello, thanks for the very nice introduction. So I'm going to talk about ultrasound imaging, particularly cardiac ultrasound, because that's what I'm experienced with, and I hope you can generalize whatever I share to other things as well. Still ultrasound, but it doesn't necessarily have to be cardiac. And obviously, I'll share my experience based on share ideas based on my own experience in grad school and here again, not to say that those are the only valid experiences, but just so that, but I'll try to be general about it so that you all can draw, uh, whatever inference you want from there as well. With that, let me just get started. And please ask questions right away, particularly if there are important key things that I have not clarified and it's sort of like obstructing, the flow of this talk, then yeah, feel free to ask questions right away. I will not mind at all. Uh, so so I will start with my reflection of like the kind of academic work that I myself did and folks in my lab did. Again, not a generalization of all kinds of academic work, just my own reflection. And honestly, the reality is you all know the groundwork that's being done in academia much better than I do. Uh, so this is more just an out of the box thinking and not really representation of all that's going on there at the moment. So what's going on here? So this is a really somewhat busy slide, but let me break it down a little bit slowly. So this was sort of like the high level flow chart describing my PhD project, with which I wrote this sort of like paper at the end as well. And essentially, my project was I was working with cardiac image analysis, and we used to have 3D ultrasound images of the heart, particularly the left ventricle. And from these 3D images, we used to extract these three-dimensional surfaces using different segmentation methods. And then we used to basically register these surfaces. But I used a graph-based framework, and then after this registration, we would get these displacements, and finally we would get this thing called strain. And strain is a quantification of basically how well the heart is beating. A normal heart will have a normal range of strain, and particularly a patient with potentially heart failure or some failure, some problem in their heart, in the myocardial tissue, will have lower strain. But the point is not here not to get into all of this, but point is I'm just trying to highlight the sort of the diversity of methods being used here, right? So the first one, this is work done by my colleague, where the segmentation was done using level sets and dictionary learning. Um, so this portion, particularly learning to represent image patches as features, I use basically autoencoders, not so surprisingly. And this was obviously neural network. I don't call it deep neural network because, as you can imagine, with patches, you don't really have to make deep neural network. Just neural networks is okay. There are graph-based methods, like I mentioned. I set up these surfaces as points in a graph, and then the correspondence, the matching, the registration was basically posed as finding paths to this graph, which was really like fun thing for me to do because since there were that was probably the part I found most exciting, to be honest, and not like just the AI and the ML components. And there's also some classical like mechanics, biomechanics, or like material mechanics, whatever we want to call it, which where it was just some deterministic, differential algebra, basically to go from displacement fields to strains. So essentially, what I'm trying to highlight here is until like 4, 5, 6 years ago, when I was in grad school, let's say even like my mid-year, like my third, fourth years and so on, yeah, things were still pretty hybrid, and there was a lot of like mixture of different kind of techniques and methods to do this sort of work. And the main point, before moving forward to like now, I want to also like let me give you an example of what. Uh, did anybody have a question, by the way? All right, I will keep moving on. So essentially what I was trying to do was here, in the left, you can see represent like the ultrasound image of like a moving heart in 2D. So it's a 2D slice to the 3D image. I mean, this could have been originally a 2D image as well, but the point being, here you see this heart that's like contracting and expanding. The dark portion in the middle is like the blood that the heart is pumping out, and what we're quantifying is the wall, how much the wall is thickening, like in radially in this direction, and sort of like relaxing, thickening and relaxing, right? And as you can see, this is mostly a normal heart, so you see like mostly normal expansion and relaxation pattern. But if there was a problem here, we would be able to see that some of these curves would look quite different, and with this sort of information, you can make diagnosis. Uh, moving on, sorry. So yeah, but moving forward, as you all may be very well aware of, these days I think a lot of this sort of work has been is becoming more and more AI driven as we collect more and more high quality data. You can, it seems like we can construct much powerful and generalizable algorithms with like fully like end-to-end AI based methods than your sort of like this hodgepodge of different sort of hybrid. Not to say that that's the hybrid approach is not applicable anymore. It's still like we'll always face novel classes of problem where you will have no data available, and hence you cannot make any sort of statistical method in that novel problem. But in a well-defined problem where there's plenty of data, it just seems more and more natural that you can use statistical method, and particularly deep learning these days for these computer vision problems. And I like to say like the two canonical problems with medical image is registration and segmentation. Again, I don't know what most of the people in this call, what your background is, but this is probably quite familiar to you as well. There may be different sort of representations of it, like the segmentation could be semantic versus sort of like not semantic, like object detection, bounding box, right? Registration, like there could be different names for registration. Some folks call it tracking, matching, but still, at the end of the day, you wanna detect objects, and you wanna also match objects through time or through domain. Sometimes there's a cross-domain registration as well that's important. Uh, but in general, these are the canonical problems in medical imaging, and segmentation has always been more AI driven because it's a more well-defined problem in many ways. And you may all be quite familiar that the classic UNIT paper actually comes from the medical imaging community. I was actually, I believe, in fact, present in that conference where this paper was presented. At that moment, none of us knew like, oh yeah, this UNIT thing would be so popular, but obviously many years later, I'm none the wiser. But and similarly, some folks, and this another paper that I really like, and that I've used this method, and again, you all are probably more familiar with this framework than I am, but there was until like a few years later, it used to be harder to do registration with a purely like statistical method like deep learning, but these days the popular deep learning packages include like this step where the spatial transformation step is now you can do back propagation with it. Therefore, a lot of these registration methods can also be now data driven. So overall, a lot of advancement in the field. Here again, from my own old lab, I have some examples of work that folks did. And when and more with, again, more computational resources and data, folks are, let's say, now doing, including, let's say, temporal information as well, much more than before. Obviously, it was there before as well, but now it's not like even a big deal, including things like attention, which to you all may seem like trivial things, but I'll contrast that with industrial work where we're still not, let's say, doing super advanced AI in some ways, and we're still doing a lot of work in 2D. And So this is just an example where segmentation with like temporal information and attention improved results. This is an example again from my colleague uh, where just doing a unit was not very good, particularly in along this axis. You can see that it misses a lot, whereas as you add this temporal information nicely with attention, your results tend to get better, right? So any questions at the moment? All right, I will keep going. Yeah, another thing we're seeing is more and more of end-to-end network. So the very first visual that I showed you, like the flow chart I showed you, basically had the segmentation and the registration steps removed. The segmentation was done independently, and the registration was done independently. Whereas here now, more and more, you're essentially you folks are doing both of these steps together. You basically have a multitask framework where you have two images, and if you have the ground truth segmentation for those pairs of images, you can predict that as well. And but you can also predict the displacement and do the spatial transformation, and then align them and get loss from that as well. More, I don't know what my colleague did here, but for instance, one thing he seems to have done is perhaps sharing some weights to make sure the features they're using are somewhat like they use similar features and they learn from each other as well. There's another way to sort of like directly combine these two things where you can add a loss where one segmentation mask is also transformed by the same displacement, and you can then calculate the loss between the transform, like the predicted segmentation mask by the displacement, and the real segmentation mask for which we have ground truth for. So you can just basically, yeah, more and more you can do so many of these things nicely with like, AI-based tools. And it's not like we didn't know we could draw out these sort of diagrams when I was a grad student. Like I could draw this out conceptually, but I could never like we didn't have, at least at that moment for myself, I didn't have the tools to do that, resources, and also perhaps I wasn't skilled enough to be blunt. Because I imagine some people were already doing that kind of stuff on their own, but I didn't feel like inventing a whole like class of methods just to do this sort of stuff. But yeah, it's cool. Like now, more and more end-to-end work is being done like this. And yeah, again, nice just examples where there's this on the left we have uh, without this joint framework, and on the right with joint framework. As you can see, I think the green is the ground truth and the red is the prediction. It's much more improved. Here, a different axis as well. These are short axis and this is long axis view, just slicing the heart, from like the top or or sort of like the side. Uh, yeah, it seems to be better for this as well. So overall, yeah, I think more and more end to end and so on and so forth. Cool. Let me just recap what I think of like academic works. This is again my personal reflection and a little bit of outside of the box sort of opinion for you all. So I think honestly, generally, academic work is technically more advanced. I've already mentioned this, so I'm not going to get into more of this. It's less validated. Again, it's just by the nature of things. Like in for us, in industry, we have to meet the FDA's bar, and the validation and statistical analyses that you have to do is really like rigorous. Obviously, some companies do it better than the others, I imagine, but I have found like the FDA's bar and like rigor to be pretty good. In fact, we've had to oftentimes do multiple iterations of like submission, or respond to their feedback and like questions with regards to like the evidence if they're not happy. Uh, So, but yeah, in academia, because you don't have to do that, yeah, it's like not so well validated in a large scale data. And because of this, that, like uh, it's may not be so scalable. Like you could have some really like cool state of the art algorithm, but if it was only tested with like 20 patients and like 80 image volumes. It may be like pretty nice, to publish and stuff, but a company or like another third party, institution cannot like then jump on it and be like, well, we can make like a really like amazing product out of this. That's because it's a risk factor. Now this is the so this less validated is like just by design. It's not really like it's not a flaw, but maybe this one is a little bit of a flaw in my opinion. I think this is a bit of a problem where uh, like since the funding is generally available to solve like these cool technical problems, sometimes like really boring user needs are not thought about. For instance, this is one something I heard constantly when I was both a student, like once I went to a hackathon, and uh, a product addressed this problem where they designed like a at least in like a not like a real prototype, but like like computer like SolidWorks or something. They designed like a really nice ergonomic probe, and then we came up with some really cool AI. But at the end, I think their product was much better, well received than like ours because this solved like a much more acute problem. And this is a crucial point, and I really genuinely did not see a lot of work based on the acquisition aspect of the image. So unlike your standard other imaging modalities on ultrasound, because it's a handheld device, it's really like noisy. Uh, it requires a lot of expertise to perform the ultrasound well and also understand it. So oftentimes, like I've worked at this point, I've seen a lot of data out of like hospitals and stuff. Like the average quality of the data that's being acquired in clinical world is pretty poor, to be honest. And that's because the companies and also academic institutions are not prioritizing this problem. Where how do you even like help people acquire good images? And honestly, if you don't acquire good images, everything else that follows is like sort of like moot point. So this was something I struggled in grad school as well. Like I was working on like my algorithms, but then the image quality was so variable, and we just sort of assumed that that's what it is, to be honest, at that point, until I joined my current company, and where our like major goal from the very beginning was to focus on the acquisition aspect. So that helps me transition nicely to the sort of my now impression of the industry work. Uh, any questions again at this point? All right, I will keep moving then. So I've already mentioned, I'm just gonna try to go through this a little bit quicker. But yeah, in the industry, I found that folks are pretty seriously taking both the acquisition and the interpretation parts. The acquisition is acquiring good images, and interpretation is once you have the images, you wanna like then do all sorts of predictions on it. Because when you're selling a product, like let's say you have a product that calculates ejection fraction, right? Like a nice algorithm. But if people are just feeding junk images to it, you're allowing your product to fail as well. That's why you want your product to then also produce good images, so that even if you have like a cool like prediction algorithm, this algorithm itself benefits from having like good images as well. And the quality, and here I've written this part, quality assessment as an interpretation as well. And this is also a crucial factor, right? This is also something I noticed I didn't focus too much back then, or I wasn't seeing academia focused back then. But similarly, just similar to like similar to the example I mentioned above, like if you have a cool algorithm, but then you have no way of assessing the quality of the images coming in, you will set yourself for failure, because you will start predicting values on really poor images as well, and then you will start getting really bad errors, and you're just basically shooting yourself on the foot. So when you're like, yeah, really making product out there for people, you have to think about these sort of things, and naturally, I suppose, yeah, you start being aware of these sort of issues. So overall, to recap, I think at a very high level, we think a lot more about the acquisition piece as well, because ultrasound uniquely is different, and you have to think about building algorithms that help, non-professionals or even professional, but who's not very good, like use the ultrasound probe, maneuver it nicely, and capture good images. Uh, so let me just give you some examples. So this is our product demo for the company, Caption, the company I'm currently at. I'm going to fast forward a little bit. Can you all hear the sound? I'm not sure. I don't think you hear the sound from the system, but don't worry about it. I'll just sort of explain what's going on as the video plays. But essentially, what we're looking at here is Sarah, our sonographer, is scanning a patient. It's not really a patient, but like a patient model. And basically, this image gives an indication of how the probe should be oriented. This gives an indication of what an ideal image we call it the parasternal long axis image of the heart of the left ventricle particularly looks like. And here you'll see the actual image you're producing at the moment. Here, this is like we call it like a quality meter here. Like if it crosses this threshold, it means it's a really good image. And you'll also see instructions on how to move the probe. So all right, we'll just watch the video. Yeah, that's the positioning, the reference image. Yeah, basically these are the AI components, the quality meter and the these text and visual based indicators. And yeah, once the user captures an image, it's automatically recorded, and then it moves on to the next image. So yeah, basically I actually worked on this project, particularly the these text-based instruction portion, and it was a really cool project to work on. It was really cool to see this empower like people capture images. And myself, I didn't know how to do ultrasound, but using the thing that I myself built, I was able to capture like nice images of like the heart, and that could be of pretty immense diagnostic value to clinicians. And when we did it, like I think when we did the FDA, did the clinical trial and submitted to FDA, at that moment it was probably the only product like validated having this sort of system. But I think at this moment there are other products as well. But it was pretty cool to be part of this project, and I really felt like solving like a really nice problem. Uh, and like I mentioned, the AI components were the quality meter, where you're seeing the score of the image in real time, and then the text and image-based instructions. So these two work hand in hand, and they basically guide users to acquire nice cardiac ultrasound images. So just another example. This is a product by another company that we actually collaborate with, Butterfly Networks. They make ultrasound probes, and they have a different approach where they are using teleguidance. They're using remote expert assistance. Again, I'm not this. The point is to highlight that companies take this acquisition piece much more seriously, and they understand that if you don't acquire good images, everything that happens downstream, like the rest of your AI, is like pointless. So let me fast forward a little bit as well. It's a handheld device. It just needs to connect to your iPhone or Android or tablet. And yeah, once you set up the teleguidance, you can connect with an expert, and the expert can give suggestions. And obviously, I can see there will be limitations of this approach where you don't have reliable internet and stuff, but in situations where that's not an issue, this approach can work as well. And this approach can work sometimes, let's say, in like tricky situations where you'd have to need expert guidance, because sometimes, depending on the situation and patient, like doing the normal imaging might be pretty hard. And now I'm just going to give a couple examples of the interpretation work that we have done and some other companies have done before I wrap up and leave time for questions. But essentially, as I may or may not have mentioned before, ejection fraction is basically a measure of like how much the heart is how much blood is being pumped out by the left ventricle. The left ventricle, yeah, it's constantly, pumping the blood out to your entire body, and roughly at every instant, it pumps out about 60% of the blood. So generally, a person with a weakened heart, with some problems, typically the pumping efficiency of the left ventricle goes down. Hence, they can only pump out, let's say, 40%, 50% of the blood, and sometimes in really severe cases, 30%. So this is actually like the most important, I would like, or at least the most widely used indicator of like your LV function, right? The ejection fraction. And yeah, so this was also another FDA approved algorithm for by Caption where I work. And the cool thing about this is typically the prior methods were able to do this only from apical 4 and apical 2 views. Actually, they needed to have both of these together, whereas with our method, we can do it from any one of the three, like the parasternal long axis view, apical 4, apical 2 views. Essentially, if you're confused about what these views are, yeah, the heart is a three-dimensional organ, but where you image from, these 2D slices could be taken from different angles, and there are these standard 2D slices that you image. And essentially, this product helps you capture this quantity, ejection fraction, from these different angles. And we also provide an error bound. Again, this is a really important thing that a lot of clinicians like. If you just give a value, what does it mean to them? What about the confidence? Should they rely on that value or not? So working on things like this is also really crucial. And hopefully, the algorithm you've developed can naturally produce like this sort of confidence metric as well, the AI algorithm itself. And another really important measure of the heart at the very beginning, I talked about strain a little bit, the measure of like the valve function. So this is crucial because you can have certain situations where the LV is still pretty efficiently pumping the blood on aggregate, but certain part of the LV could be beginning to develop issues. For instance, let's say at the moment you have some problem only localized to, like, let's say the top part, the apical part of the heart, whereas the rest of it is okay and your ejection fraction is normal. You could still have a heart that is like about to have a very serious like injury, like basically heart failure, right? And this situation is called heart failure with preserved ejection fraction. And it has been shown clinically that looking at this metric of strain, which is a measure of like how much the heart muscle itself is contracting and expanding, as opposed to the entire like left ventricle, like the blood pumping efficiency. Here we're looking at the muscle contractility, right? Slightly different things, quite related, but different things. Then you can, once you track that contractility, wall contractility, it has been found that that's an early indicator of like heart failure if it's not normal. Same thing, it's just done from like a different 2D slice. Earlier I mentioned the heart is sort of cylindrical, 3D organ, but where you slice it during imaging, like is it like this sort of like a cross-sectional 2D slice, or is it like a longitudinal 2D slice? So this is more of a cross-section across that's why you see sort of like a spherical kind of shape, as opposed to here it's a longitudinal sort of shape. And yeah, because it's a spherical kind of shape, here we calculate circumferential strain. And similarly, this is also quite crucial. Yeah, just to wrap up my opinion on industrial work, the good thing about it is there's better validation. So I've already mentioned like there's less of a technical sophistication, not because we desire to be less technically sophisticated, but if you go out there in clinical practice, the reality is still nobody's really using 3D imaging. or very few institutions are. So if 90% of institutions are still doing 2D imaging, why would the industry waste their effort in developing all kinds of 3D algorithm? That's just the reality of how things are. But in general, there's better validation, and of course, you have to validate, you have to submit your results to the FDA. But I think companies are now getting better in terms of producing scientific literature as well, contributing the writing, contributing the evidence, using that evidence to write scientific paper and basically invite peer review on and critique on their approaches and their method, right? So I think companies are getting better. Again, not everybody. This was a big criticism of that, industry never like publicizes their data and doesn't like, communicate their data and their methods to the scientific community. I would say it's getting better to some extent. So for well-defined problems with lots of data, particularly ejection fraction, like mentioned multiple times, a lot of really good algorithms are coming out at this moment. There are like multiple companies that do that calculate ejection fraction, and like I think the reliability will obviously vary, but at least it's happening, right? And it's pretty good. But of course, the flip side is that for problems where there isn't a lot of data, and where it's a fuzzy problem, it's not well defined, then it's still like hard to. I'm still not seeing a lot of like cool new algorithms and AI-based methods coming out. It's a bit of it's slightly due to like regulatory concern as well, because you like for instance you can let's say you develop some algorithm, let's say you can make a small little tweak to it and then generalize that to like to some transfer learning, for instance, and apply it to like a slightly different but related problem. But to the eye of the FDA, it's a whole new problem and it's a whole new product, right? That's why they wouldn't be happy like saying, oh, we just made a little tweak. Are you going to be happy with like a very minimal like validation effort? No, that's not how it works. So it's hard to generalize because of this. So what needs to happen is this is sort of like my final point is that for folks here who have aspirations of doing like work in the industry, or honestly even academia, where if you want to have like really good impact, you want to find like these sweet spot problems to work on, where the problem can be you can use AI and automate certain predictions reasonably well, but again doesn't interfere with the clinicians like workflow, their intuitions, and they don't feel like challenged, right? Like there are some really like for instance there's this pervasive idea that like radiologists like so much of like radiology is going to be like replaced by AI, right? And that is obviously not like a good situation, because the radiologist will then have a very adversarial attitude towards AI, and then if you cannot cooperate with the clinicians well, you cannot produce good algorithms. So it's this like problem. But for instance, some companies have approaches to get around it, right? There's this one company I can think of, they're called ContextFlow, and they work in radiology, where they're not really doing any like specific prediction per se, but they're doing image retrieval. So what they do is they can pull up all images that look like this one image that you have. Then like the radiologist or other clinician can look back at the previous history and previous like diagnoses, and then sort of like find out similarities. And so there are clever ways of like integrating in that workflow and like integrating in that problem sphere, and not being adversarial and having conflicts with clinicians. But the paradox a little bit is that AI is oftentimes good at what human is also good at, right? Because that is the reality, because you need good data to produce good results, good AI-based results. But then obviously there's good data means the humans are producing this good data, right? So again, you need to find this sweet spot where your algorithm is perhaps some sort of mixture of like supervised and unsupervised. Let's say you have some like fully labeled data, some like not fully labeled data, and you're leveraging certain intuitions and ideas, which then help you solve problems where there's very little data or poor data as well, right? So you want to like find these sort of problems. And I think for me, we were fortunate that the acquisition problem was not well addressed. Nobody was really honestly had a good solution for that, and and it really did not interfere with anybody. We were sorry, we were marketing that for not well trained folks to use it. So again, it doesn't hurt like it doesn't sort of like interfere with like the expert clinician's workflow. Oh yeah, sorry. So yeah, last point is that yeah, clinicians like clear, precise, like small measurements, like and quantifications, like what is the size of the aorta, what is the size of the LV, what is the ejection fraction. But if you start saying, oh, the LV is enlarged, and this patient may have I don't know, I'm just making stuff up, but this patient may have atrial like fibrosis or something, right? Then you're making a diagnosis. Then you're like sort of becoming more confrontational with the clinician, like with the doctor, and and the reality is that's not well accepted. You can again have come up with clever ways of like augmenting and integrating in the system as opposed to being sort of confrontational. Yeah, and overall, yeah, it's obviously challenging to find these like problems and stuff, but ultimately it's pretty rewarding to, get there and like apply it and sort of be impactful. I have some more on appendix if you're interested, but I think at this moment I am going to stop and pause for questions.
Hey, thanks so much for a great talk. If folks have questions, feel free to enter them in the chat if you're shy, or feel free to butt in also. You can unmute yourself. I did have two questions myself, just to
Hmm.
start things off. You showed a video where you showed this quality meter for imaging, and I was just
Yes.
curious how quality was defined. How did you score quality? What was a good quality? What image got a high score? What kind of image got a poor score? And how was that labeled?
Yeah, very good question. Yeah, very good question. Let me, without getting into the specifics, which I cannot divulge, there are a couple different ways of addressing a problem like this, right? One could be, so for instance, with echocardiography, it's such a standard thing. There is this one particular metric called the ACEP rating, ACEP rating, which is a very well established rating system of quality. With all your There are these 10 standard like 2D slices, 2D images views of the heart, and for each of those, the guideline for what is a good image, it's like pretty well defined. So if you collaborate with expert clinicians, they will be able to give you pretty good rating on sort of the quality. Obviously, then, but this is a well-defined problem, and you can do something like that in this well-defined setting. But if that is not the case, then you want to come up, maybe this is a novel problem and there is no such standard. In that case, you want to come up with your own sort of rating, but obviously you wouldn't do that yourself. You would continuously work with clinicians, get a lot of feedback, and iterate with them multiple times to come up with a consensus guideline, right? Then then you would then ask clinicians to follow this consensus guideline very strongly that you have developed working with them. And I've had to do stuff like that because I started, even though today I mostly talked about cardiac, these days I mostly work on a lung project, lung imaging. And for lung, there's very little like prior work in terms of like these sort of things, quality. So we've had to do it ourselves. So yeah, but essentially you do it yourself with collaboration with clinicians, and you collect much more. For every data point, you collect like at least 3 to 5 labels, right? So that when you average it out, you have stronger results and confidence. So essentially, yeah. So Answer is sometimes there are standard things you can do and follow, but sometimes you would have to come up, slowly develop that yourself.
Awesome, awesome, thank you. We have a question from Shireen Khan, and the question is, I understand that there is a type of ultrasound device that connects to a smartphone. Would clinicians be
Yes.
more amenable towards different interventions or telehealth applications? And I guess she's thinking specifically of applications for aging in place.
Sorry, I did not catch the last part. Applications for what?
Um, I'm not certain.
But
The last.
yeah, so this is an example of a proof connected to just your smartphone, right? As you can see right here, right? So I didn't understand the question perfectly, but obviously this is they're doing exactly this where they're using teleguidance from an expert uh, to then acquire these images and also not just acquire, like, I mean, if you can acquire, you can also then the expert can make a recommendation and like diagnosis, right? I remember specifically with this company and their devices, they had a lot of like examples where in COVID, a lot of clinicians themselves were sick, right? And they were at home and but they could not they would just scan themselves, but then uh, and not everybody is a pulmonologist, right? Even though they could, maybe somebody's a orthopedics doctor, and they're reasonably qualified to use the device, but they're not an expert in lungs, so they can then send that to their lung colleague, and they can do diagnosis. So yeah, there's just like loads and loads of application, and the thing to remember is the only thing I would say to add to that is you want certain algorithms to live on the device and certain algorithms to be delivered through the cloud, right? You cannot rely on the cloud for everything, right? Like the simplest of things you would have to deliver on device. So that makes the problem like more challenging and interesting as well, because your algorithms have to be lightweight and like very responsive. Like you have to have high like throughput, right? Uh, but for things you can do in the cloud, yeah, there's like you can be a little slower. Obviously, even though this is cloud delivered, it's still real time. This sort of teleguidance. Uh, Anyways, hopefully at least I touched on something that was satisfactory.
This is
No.
Shireen. So the question was specifically about age tech and aging in place because we have a very large growing elderly population and we have a declining number of healthcare workers and it's
Hmm.
also very expensive. So the idea was really maybe if it wasn't someone who had medical knowledge where they could kind of maybe be managed a little bit, manage their own condition by not without leaving the house, like what the
Yeah,
applications are for
yeah,
that for
I
now
see, I
and
see.
for the future. Yeah, thank you.
I see. So thanks for the clarification. Yeah, so very good question. Yeah, we actually did a pilot with a company. I don't know where that went specifically called Zifficare, which I believe it was exactly this sort of situation where they are doing monitoring for like at-home patients, particularly elderly and perhaps folks with chronic conditions where obviously, they have to be monitored, but they're not in the hospital. And yeah, we trialed with them where we actually they have like a box where they have a bunch of like testing equipments where they can collect vitals, they can collect other information, and
Hmm.
they can also we did a trial with them where they also do the ultrasound. And yeah, folks then remotely then go to the people's homes or like nursing homes and
Hmm.
do the ultrasound examination with our system. Obviously, it's still, this is still not for like anybody, like it's still with, let's say, for like nurses or medical
I see.
assistants, for folks with some clinical background. But I imagine more and more things will become available for even like the general public.
Okay, great. Thank you.
Thank you. Great question. Um, yeah. Yeah. Anyone else have any questions about anything, even the FDA approval process, or even some of the work that Nripesh has done? I did have
Yeah,
a question.
mhm.
Oh, sorry. Quick question about Caption Health. You were saying about how a lot of these healthcare companies value the acquisition just as much, if not more so, than even the downstream analysis.
Right.
When Caption was first starting out as a company, were they primarily focusing on acquisition? And did the data science team kind of join in later, or were both teams kind of collaboratively working together from the start? Um,
Well, I think I understand your question, but when you say the data science team joined the acquisition, well, the
well, was the
acquisition,
primary product the was the primary goal acquisition first for the company, and
I
then
think it was from the, well, I don't know about the extremely early days because I
yeah,
wasn't there, but yeah, from the very beginning, they realized that this is like a big sort of unsolved problem, and I mean, this required ML work, and the ML team or the data science team, we were primarily focused on this from the beginning.
okay, okay, sounds good.
Yeah.
Yeah.
What are some of the
Uh,
other sweet spot problems that currently exist in industry that are
ooh.
non-confrontational to clinicians
Well,
and
that is for you all to figure out and start a company. Well, it's a very good question. I think clinicians really like clearly defined like measurements, right? I can give some examples for the heart or the heart, let's say, because it's more well-defined problem. But you can extrapolate. Well, with ultras. So, for instance, like any sort of measurements, to be honest, right? And that hasn't, if the product isn't out there, for instance, the inferior vena cava, the IVC, I guess it's a vein, and it's in clinical setting, like in emergency and other critical care situations, when patients are being fed the fluid, when you're getting like saline fluid, if you over salinate people, their veins might start dilating. And that can have a pretty severe consequence, right? You can start getting like effusion and stuff. So tracking that and like producing like numbers, producing some results for that, for instance. But I mean, we are trying to do that as well. That's another example where it's like clinicians like, yeah, like well-defined, narrow scope thing. They don't like you coming in and doing like a very broad prediction, which is, well, that's how things are now. It could be different in the future.
Do you think it'll change in the future with how clinicians respond?
Well, yes, and yes, I would say yes to a certain extent, because, well, with anything, if you're trying to do a complex measurement, like the burden of proof on that will be much higher, right? The FDA will scrutinize whatever evidence you generate much more strictly. But then if you're able to generate it, right, if you're able to solve the problem reliably, then of course the FDA will have to approve it, right? Because at the end of the day, if you demonstrate good evidence, it is what it is. You can't be blocked. Also, as Serene, I believe. Sorry if I didn't
Shireen.
get that right. Serene. Yeah, sorry. If as they mentioned, like the telehealth model, right? A lot of like healthcare delivery strategy itself, I think, will change in the future. It wouldn't be so tied to like, these centralized entities. For better or worse, it is going to get more decentralized, and different sort of players with different sort of incentives will come in and deliver service. And you can say like a doctor may be disappointed, a doctor who works at like Stanford or like some elite institution, but then somebody else will come up and they will deliver that AI-based service. And uh, one, I'm not advocating that that's a good thing. In fact, I think that could be quite problematic as well if not well regulated and done like haphazardly. But yeah, that's, I think, the marketplace will become even more decentralized and like fragmented. It seems to be going that way. But again, this is sort of more business direction, and I shouldn't comment too much.
Can you can you expound on that? I was actually going to ask you. So my assumption would have been that university clinicians would be more interested in what you're doing than like a hospital setting, regular hospital setting, but it sounds like that's not true. Are there any
Hmm.
segments where people are just more amenable to, because especially we don't have enough doctors, I'm sure everybody understands that they all want to quit. So it's
Hmm.
a problem for everyone, it's not like somebody's going to take their job. We don't have enough doctors.
Yeah, so I mean, honestly, this could be slightly controversial, but what I've experienced is obviously the university-based doctors of more, your big, yeah, they are they're quite interested in like sort of big like research kind of projects where it's, let's say it's a big clinical trial and it's a big, research
Like
project with like
funding, because of funding.
uh, funding, and it's, you could say, scientifically more interesting as well,
Okay.
technically, right?
Hmm.
It's
Yeah.
it's more stimulating to them to work on,
Yeah.
oh, this new catheter, right? Is it going to work or not? Like, it's quite a remarkable thing to be part of.
Mm.
Uh, whereas they would not be so interested, let's say, to be very honest, like in working on this little thing that could really like impactfully impact people's lives, but like it doesn't seem that much like
Mhm.
interesting technically and scientifically. But it is what it is. It's sort of, unfortunately, those incentives are not well aligned. I'm not saying that they should
Mhm.
do what we are saying we should, but it's like, I think in an ideal world, like these two incentives will align and it will produce good results.
Is there government involvement in kind of fomenting the research, like pushing the research forward? Or monies or just some kind of task force? That's
Yeah, so the government is obviously, when you say research, obviously the government funds most of at least the academic, like
Mhm.
scientific research, right, clinical research. So obviously yeah, they obviously have big vested interest in in trying to see, like, make sure that that sees light of the day, right, and not that just doesn't become a paper somewhere and like it sort of impacts people's lives. So the government, for instance, even our company, our some of our initial grants was through the government. Our co-founders were academics, and they got NSF grant to even like start this up, like bootstrap this, right? So the government is obviously interested and motivated, but again, I think some of it is like the technology and like the market forces change so fast, and then these institutional behaviors are always slow to catch up, right? The institutional attitude of like your big hospitals and like your the FDA and the government is slow to catch up, and most of it is for good reasons. FDA should not be changing its policy every other day because
Mhm.
then you can never build like sustainable business if that changes so much. But I think some of it is just like dynamics of like things, technologies. This sort of technology has been disruptive for a while, and as we've seen in other species, and it's going to happen in medicine as well.
Awesome. Um, Thank you so much. Thank you for a great presentation. Thank you for taking the time to answer our questions. Um, yeah, thank you all for attending. Is there anything else, Anthony, before we sign off today?
I think if anybody has questions in the future for Nripesh, maybe reach out to Karthik and I via email, and we can forward those to Nripesh.
Yeah,
Yeah.
that
And
works.
we'll
Thank
have
you.
our
Thank you all as well. I unfortunately could not present a whole lot of technical material because I wasn't allowed to, but I tried my best to keep it interesting.
Yeah, that was great. Thank you so much.
All right, bye bye.
Yep. Bye. Bye.